I like this table. This table really helps clarify a few things for me. So here we're relating delta G to delta H and delta S. So we can do all of this using our equation delta G equals delta H minus T delta S. And all we're doing is positive and negative signs here. And remember, spontaneous means when delta G is negative. All right? So let's see here. For this first one, delta H is positive. Okay, so that's not spontaneous. Delta S is also positive. So what we need here is at low temperatures, this negative is not going to be enough to overcome delta H. So that's going to be positive. Now when we get to high temperatures, look, see, here's the negative sign. When we get to high temperatures, T delta S is going to get high enough to overcome this positive delta H. So delta G becomes negative. So I like to refer to this as spontaneous at high temperatures. Now high can be relative, and remember that spontaneity is not necessarily related to speed. Okay, next. Delta H is positive, delta S is negative. Okay, so we're going to have a positive delta H and a negative times a negative. So no matter what we do, delta G is always going to be positive. So this is non-spontaneous. And temperature doesn't matter because that's always going to be a positive. Positive plus positive is positive. Non-spontaneous at all temperatures. Okay? Now, next one. Delta H is negative. That's good. And we have delta S is positive. So we have a negative minus a positive. Delta G is always negative. So this is going to be spontaneous at all temperatures. Because it doesn't matter what we're doing, our second term is always going to be negative, and delta H is negative. All right, last case, delta H is negative. That's good. In this case, delta S is negative. When delta S is negative, negative times negative is positive. So at low temperatures, the negative times a negative isn't enough to overcome our negative delta H. So then when we get to high temperatures, this positive term overwhelms delta H. So remember, delta H is not related to temperature for our purposes. So this here, we do have a negative delta H, so it would be spontaneous. And it's going to be spontaneous here at low temperatures. Moving on here, let's go ahead and discuss the conditions when each reaction is going to be spontaneous. So we need to consider delta H, and we need to consider delta S. So going from gas to liquid, going from gas to liquid, that's going to be an exothermic process. So delta H is negative. Condensation releases heat. Think about sweating if that's difficult for you. And now delta S here, gas to liquid, that's getting more ordered, so delta S is also negative. Look back at your table. Negative times negative is going to be spontaneous only at low temperatures, which your phase diagram actually shows that. Next, going from solid to gas, this takes energy, so delta H is going to be positive. And by going from solid to a gas, we're creating a lot more entropy, a lot more disorder. So when they're both positive, that occurs spontaneous at high temperatures, as we know. All right, here we're going from gas to gas, but we're splitting a bond. Bond breaking always takes energy. Bond breaking takes energy there. Delta S, we're going from 1 mole to 2 moles. So delta S is also positive. So this is only going to happen at high temperatures. Now here they help us out because we wouldn't really have a way to know this other than if we flip back on our first page, because we use this equation as well. So it tells us it's endothermic. So that means delta H is positive. Delta S, we're going from 2 moles to 3 moles. So that's going to be delta S being positive. When both of them are positive, oh no, sorry. No, that's right. Yeah, 2 to 3, and they all stay gas, so delta S is going to be positive. So this is going to be spontaneous at high temperatures. At high temperatures. And let's go ahead and look at this one because there's not really calculations involved. We're just going to discuss what would have a higher entropy. Carbon monoxide versus carbon dioxide. This is the larger molecule, so larger and more complex molecules have greater entropy. You can think about when you break them apart. Here we have the same substance, methanol, and from liquid to a gas. Going to be the gas. Gases always have more entropy than their corresponding liquids. Argon versus carbon dioxide. It's going to be carbon dioxide because you can make the argument that it has a higher molar mass. So you can say it's a higher molar mass because that's correct. You can also say it is an element versus a molecule. Remember, molecules are naturally more complex, so they're going to have greater entropy. But this would also work if you had something like water that had a lower molar mass. All right, now here we have two different compounds. They're both in the gas phase, so we need to consider this one. You can look at your periodic table because this one has the higher molar mass. And oh, there's one more that snuck off the page. NO2 versus propane is going to be propane because it is the larger molecule, meaning there's more bonds in it, so it's going to be more complex.